This is a lab video that goes along with Lab 15 in your packet. It's called All About Solutions, and we will be doing Part C and Part D. So if you want to get the procedures out for Part C and D, along with the data pages for C and D, that will help you get ready for the video. Now, as the complete lab packet would include pre-lab questions, numbers 1 and numbers 4. So pre-lab questions 1 and 4. The data and any observations and calculations for Part C and D. If I could spell calculations right, you guys know that's not my forte. Calculations for Part C and D. And then we're also going to do reflective exercises. At the end of the lab, we're going to do questions 9, 10, 11, 13, and 14. So a total of 5 reflective exercises. So once you've watched the video to get the data, you've completed the pre-lab, the calculations, and the reflective exercises, then what you're going to do is upload your assignment into Lab 15 in Canvas. Now there's 2 formats that I'll accept. A PDF file, which would mean you would need to either scan it in a scanner, or if you don't have a scanner, I recommend getting an app on your phone like Scanner Pro, and then you take a picture of it and it converts it to a PDF file, and then you can upload it into Canvas. If that's not an option for you, the other option would be to type the answers to the pre-lab questions, the reflective exercises, your data and calculations into a Word document, save that, and upload it into Canvas. Please do not send me emails with your completed lab work, and please do not send me pictures of your completed lab work. All right, so what we're going to do is our objectives. We're going to apply the golden rule of solubility, which we'll talk about that when we get there. We're going to calculate the concentration of an unknown solution. And so we're also going to determine the concentration of an unknown solution. Part A and B involve osmosis and dialysis, and so these objectives, we will not be doing. So let's get started. So this is Part C, and it does take a lot of test tubes, but it's not particularly challenging. So what we're going to be doing is we're going to have, you see here, label 4 test tubes, which I did. You'll see that in the picture. Next slide. And to each test tube, I'm adding a pea-size amount of the solute. And so we have the solute is the substance that generally is in a smaller amount, and this is what is being dissolved. We're going to try to dissolve this. And so we have 4 different solutes you can see here. We have sodium chloride, which is ionic, metals and nonmetals. We have sucrose here, which is covalent, and because of the oxygens, it is a polar covalent molecule. I'll put polar C. So polar, just remember that is created when the electrons in the molecules are not distributed evenly. So there's different parts of the molecule that might have a partial positive or partial negative. So when you have carbons and hydrogens and oxygens, those oxygens are very electronegative, and in those types of molecules it tends to be polar, and the electrons not distributed equally. Then we have naphthalene, and naphthalene is what we call a hydrocarbon. Naphthalene is the active ingredient in mothballs, and so it has a very distinct odor. Now, hydrocarbons, things that only contain hydrogens and carbons, are nonpolar substances. So it is covalent, but it's a nonpolar covalent compound. Carbons and hydrogens, their electronegativities are almost identical. So when carbons and hydrogens form molecules, they are nonpolar molecules. And then finally we have vegetable oils, and oils tend to be a mixture of hydrocarbons. So vegetable oil, while it is a liquid, it is also a nonpolar covalent substance. So I had 4 test tubes, each with a different solute in them. And then step 3 said I add approximately 3 milliliters. First, the first group I did had a solvent of distilled water. Now the solvent in general is the part of the mixture that is in a greater quantity, and this is what does the dissolving. So the solvent is what is going to dissolve, or maybe not, the solute. So I added 3 milliliters of water to each of the 4 test tubes, and then I let them sit there, which step 4, I let them sit there for about a minute. And then I'm going to make observations. Now I also used a stirring rod to mix them. So it says here, this is your observations, this is what you're going to be looking for. If the sample is soluble in the solvent, the mixture will appear uniform. If it is insoluble, you will see solids, a cloudy mixture, or a formation of 2 layers. Okay, so what I'm looking for is soluble. Let me erase this little part so we can see. You can, hopefully you have your your procedure open so you're reading along. Soluble or insoluble. Now, in the first part of the introduction, it said the golden rule of solubility. And this is what the golden rule is. Like dissolves like. Now, this rule is not very helpful unless you know what are we comparing, what things are alike. And what like dissolves like means is that substances with similar polarities will dissolve in each other. So I oftentimes, in kind of a joking way, will say polar loves polar, nonpolar loves nonpolar, but polar does not love nonpolar. Now you might look up here and you say, well, what about ionic? Well, remember when something's polar, it has those partial charges, a partial positive and a partial negative, a separation of charge. That's close to ionic. So oftentimes ionic compounds are going to respond the same way that that polar would. Not always, but oftentimes. So let's take a look and we'll try to think of this golden rule as we go through. Like dissolves like. Remember, what we're trying to see is something soluble or insoluble. Okay, so my first example, this is with water. Let me see if I can write on the side here, water. And water is polar. So first I have NaCl. And here it is. And here it is close. And so looking in, this is a uniform solution. There's nothing left. And so we would write soluble, or your book says you can just write S. The second, number 2, was sucrose. And I want to, let me go back up to this one. So sodium chloride is ionic and water is polar. So they are similar. So we would expect it to be soluble. That's like dissolves like. Sucrose is polar. So what do we expect? Like dissolves like. So if I put sucrose in water, I would expect it to dissolve, and that's what happens. So here's what it looked like from far away. And then looking here, I look there, all the sugar dissolved. And so I would say it was soluble. Now I'm going to go through the ones specifically with water with you, but then when we go to the other ones, I want you to try to do it. So here's naphthalene. This was the hydrocarbon, and remember hydrocarbons are nonpolar. Again, this is the water that we're doing. We had 4 solutes, and the first 4 we did all of them, we added water to them. So water is polar, just as a reminder. Okay, so let's think about this ahead of time before we look at our results. Nonpolar and polar. Those are not alike, and the rule is like dissolves like. So we would expect naphthalene not to dissolve in water. And so here it is far away, and then there it is. And if you look carefully on the bottom of the test tube, there are flakes of naphthalene. They did not dissolve. And I used a stirring rod. I tried to grind them up. They would not dissolve. So we would say this is insoluble. Or in the directions it said I could just write the letter I. Now this is vegetable oil. Vegetable oils are hydrocarbons, which are carbons and hydrogens. This is a liquid. But vegetable oil is going to be nonpolar. So we expect something that's nonpolar is not the same as the solvent we're putting it in. We're putting it in a polar solvent. And so we would expect it to remain insoluble. So that's a faraway picture. Now, it's a liquid. If you look very carefully here, I know it's harder in a picture. In real life, you'd see it more. There is a line right there. So up here is the oil because it's less dense. And then there's a line, and then there's water. So this did not dissolve. Now, I know your book says soluble and insoluble. But I want to make a point here that I would have made in class. And that is when you're mixing liquids, in general, we don't use the words soluble or insoluble. We use the words miscible, which means that the liquids will mix, or they're soluble, and immiscible, which means that they do not mix and they form layers, or they're cloudy. So instead of writing, I'd like us to try to be correct. Instead of writing insoluble, because we see the 2 layers, let's write immiscible. And that we could still write an I for immiscible. Now the reason is because I'm switching to immiscible instead of insoluble is because vegetable oil is a liquid. And we use miscible and immiscible when we're talking about liquids. So let's look at our next example. So our second solvent, I happened to take a picture of it, so I put it here in the corner, is isopropanol. So this is our solvent, and it's called isopropanol. It's an alcohol, and alcohols have an OH, and so there's a part of an alcohol that is polar. But they also have carbons and hydrogens, which are nonpolar. So this can be slightly polar, but it's not going to be as polar as water. So it will also have some nonpolar characteristics. So it will be interesting to see when we're thinking about like dissolves like, which means the closer things are in polarity, the more likely they are to dissolve. So let's take a look at our substances. So number one is NaCl, which is ionic. And when I look, what do you see in the bottom? So you have to define, is that soluble or insoluble? Number two is sucrose, and sucrose is polar. And if I look over here, and I did let this sit and I mixed with a stirring rod. Look what here. Is that soluble or insoluble? Now I'm starting to see kind of a theme. I know sucrose is polar and isopropanol is not dissolving it. So I'm thinking that isopropanol is much more nonpolar than it is polar. Because again, the golden rule is like dissolves like. So then I had number three, and number three was the naphthalene, which is nonpolar. So here it is, and then if I look over here, no solid. So is naphthalene soluble or insoluble in isopropanol? I'm going to write over here just so we remember this is isopropanol still. Now, the vegetable oil, I had to do a trick because I tried to just add the isopropanol, which looks like water, to the vegetable oil, and I couldn't really tell what was going on. So I added so what I did was I took a drop of food coloring. So this is the isopropanol, which is clear and colorless, and I added food coloring, and that's why it's blue. Okay, so here on this one, I added blue to it. And then I mixed it, and you can see here what happened. And I shook it, and it's still separated. So the top layer is the isopropanol. And this bottom layer is the vegetable oil. Now, vegetable oil, is nonpolar. So it's interesting. With the naphthalene, it did dissolve slightly, but the vegetable oil, it did not dissolve. And so then the third solvent, the thing I was using to dissolve, they wanted me to try the third one, and I didn't take a picture of it, so I was kind of grumpy with myself. But the third solvent is ethyl acetate. And ethyl acetate is a nonpolar solvent. So again, thinking about the rule like dissolves like, we would expect ethyl acetate to dissolve nonpolar things, but not to dissolve things like that are ionic or polar. So the green tape represented my ethyl acetate, and number 1 was NaCl, and this is ionic. And if we look over here, we see after trying to dissolve it, there's a solid. And so your observation, is it soluble or insoluble? You got to write one down. Number 2 is sucrose, which is polar. And again, here it is right there, and I look over here. And again, I see solid settled at the bottom. So your answer, is it soluble or insoluble? Now I continued on. Again, the green label was what I used for the ethyl acetate. And it's a nonpolar substance. Nonpolar solvent. It's what I'm trying to dissolve with. And so this is naphthalene. And it is nonpolar. It's a hydrocarbon. And so number 3 here, I look here. And if I look, there is no solid. No solid. So you have to observe, is that means it's soluble or insoluble. And then number 4, this is vegetable oil. And when I look over to the vegetable oil, there is no layers. And so then I ask myself, is this miscible or immiscible? Miscible, which is spelled you can look at that. Miscible, which means it would mix, and immiscible means it does not mix. So I'll just tell you, this is miscible. That's how you spell it. So this completes part C of Lab 15. So you should have recorded in your data your observations based on the pictures that I have. So now let's look. Oh, I forgot I included this page. So I just took a picture of all the final things. I'm not sure that it's meaningful in terms of observations because they're kind of far away. But here's a picture I took. The first, everything with a 1 is sodium chloride. So here's the sodium chloride results. Here are the sugar results. Here is the naphthalene, also just so you can kind of see what they look like. And here is the vegetable oil. For each test tube shown, the first one in the series is water. The second one, the pink label, those are all isopropyl alcohol. And the third one in the series of them, the green label, those are all ethyl acetate. Sorry. And you can just look longingly at the picture of the lab room, which unfortunately had none of your happy faces in it. So I did it all by myself, and I was wishing for you guys to be in there doing lab with me. So now let's move ahead to part D. So in part D, we're determining the concentration of a solution. And this part of the chapter is part of the text is really in chapter 14, where they talk about concentration and concentration units and how to calculate concentration. Also, if you're struggling with the pre-lab or reflective exercises, they do give you the equations and go through an example in your introduction in this lab. So what we're going to do in this part of the lab is take a solution of unknown concentration, it's salt water, and we'll make measurements along the way. We'll boil off the water and measure how much salt is left, all to figure out the concentration. So normally in your problems that you would work in your textbook, they tell you how much salt you would have and how much solution you have, and then they ask you to calculate the concentration. For lab, we have to measure how much salt we have and how much solution we have. So that's what we're going to set out and do. So looking at the procedure, if you want to have it in your book, it just says prepare a boiling water bath, which I have a picture on the next slide. I couldn't fit it into this slide. And so step number 2, it says record the mass of a clean, dry evaporating dish and measure it and record it on your data sheet. So this is a picture of an evaporating dish, which looks kind of like a bowl. I cleaned it and I dried it. And so you're on your data page, you're going to record, this is the clean, dry evaporating dish, all by itself. So you need to record that for the mass of the evaporating dish. And then, so we did that. Then step 3, measure out approximately 10 milliliters. So it didn't need exactly 10 milliliters of salt water, and add it to the evaporating dish. Now in class, this always makes me crazy because if you have to read the whole thing, otherwise you mess up. It says be sure to record the exact volume of your sample on the data sheet. So this is step 3 right here. And I need you to measure with this graduated cylinder the volume of the salt water and record that in your data, on your data page. Now in this graduated cylinder, you should have 2 past the decimal, right? This line right here, that is 9. There's 9. And up here is 10. So it's 9.1, 9.2, 9.3, 9.4. That line right there would be 9.5. And so 9.5 wouldn't have anything estimated. So I would have to say 9.5 something. So you're going to have 2 past the decimal. Now look at the meniscus of the water, which is, you're going to look up in here and record your volume. All right, so then it says step 4, weigh the dish and the salt water. So after you record the volume, you do go back, pour the liquid into the evaporating dish and measure its mass. So this is step 4. So this new mass, this is the mass of the salt water plus the dish. So that includes the solution and the dish. Okay, so let's look at the next thing. So before I move this page, you should have written 3 bits of data down. The mass of the empty evaporating dish, the volume of your saltwater solution, and the mass of the saltwater and solution and the dish. So then step 5, and this is kind of a waiting game. Here's my setup. This is step 5, and I just show you various stages. I had a boiling water beaker with boiling water here, and the water was boiling, and it slowly evaporated the water from the solution. So you can see here I'm using, in this picture, I'm using a stirring rod to kind of break it up as it starts to evaporate, and then eventually after some time all the water's evaporated and I have this dry salt. If I pick up the evaporating dish and shake it around, the salt moves freely. So then I took it off. You can see here in this picture, this is from 6. I took it off the dish from the hot water bath. I dried off the bottom and I let it cool so that it was just room temperature. And then in step 7, I waited again. And so this is the dish with the dry salt. So you will need to record the evaporating dish plus the dry salt. Okay, so on step 7, you're going to record it. So now you have all your data. And so let's take a look at how we can calculate some of the different pieces. So for example, it says on your data, it says calculated mass of saltwater sample. So to calculate the mass of the saltwater sample, well, we know, and you're going to plug in the data. I just want to give you a guideline. We know that we have the mass of the evaporating dish. I'm just going to say ED for evaporating dish, and the salt water. And so if I subtract from that the mass of the evaporating dish, the dish goes away and I would have the mass of the salt water. All right. Then I also have another part in my data that says calculated mass of dry salt. From my sample. So again, let's see. Well, I measured the mass of the evaporating dish. My last step, number 7, I measured the dish and the dry salt. That was the last thing I did. So then if I subtract the mass of the evaporating dish from that, see, that would go away and I would just have the mass of the dry salt. So now in part D, you should have all of your the parts in the data section filled out. So you made 1, 2, 3, 4 measurements during the lab, and then you had to calculate these 2 things. Now in your lab, I'm looking back. I have your lab right here. On page 210, there are the concentration units. So the gives you the equations to calculate the concentration. And there's 3 units that you're going to do. There's something called mass percent. And that's when we compare the mass of the solute, what we're dissolving, to the mass of the solution. There's a mass to volume percent. And that's when we compare the mass of your solute, which in this case is the sodium chloride, to the volume of your solution. And then there is molarity. And molarity is one of the most common used in chemistry. And that's when you compare the moles of your solute to the liters of your solution. So you use those equations on page 210 to try to complete the calculations. Remember, you're not alone in this, so if you get stuck, please reach out to me, the tutors, or even some of your classmates, and we're going to get through this. So have an open mind and do the very best you can. And again, I'm sorry we're not in lab together, because that's one of my favorite parts of class.